So when we're talking about ANOVA, let's just review it briefly. Hopefully we all watched the movie from last time, so we got this, but let's just remind ourselves what we're doing. So we want to compare the variation between the groups and the variation within the groups. When we say the variation between the groups, we mean, well, how much do the groups vary from each other? And when we say the variation within the groups, we mean, well, how far apart are the data points spread in each group? Okay. So the ways that we look at it, and we can compare it, is we looked at the sum of squares. Okay. So, and there's three different sources for sum of squares. You have your total, your group, also called treatment, and then you have your error. Let me say it, write that one on there. And then we had degrees of freedom for each total, group, and error. And finally, the mean square. So again, when you look at, like, say, the sum squares total, and you're looking at the distance from each point to the overall mean, and you square them all, when you add them up, the bigger and bigger your sample sizes, the bigger and bigger that sum of squares is going to get. Even if they're not really that far from the line, just because you're adding up so many points, they will become bigger. So we need some way to scale that. And the way that we scale it is the mean square. So we scale it based on the sample sizes and number of groups with these formulas. So it's just each sum of squares divided by its respective degrees of freedom. And finally, we need some way to measure the variation between the groups and the variation within the groups. We decided that one of the ways we can do that is we can do it with a ratio. And so we'll divide variation between divided by the variation within the groups. And the way that we do that is mean square group over mean square error. So that's what our test statistic is. So when you think about this, mean square group over mean square error, okay, let's scroll back up to this first page where we had two box plots, sets of box plots. Okay, so box plot set A, box plot set B. Which one of these did we decide is more likely to have not equal population means? B, because the box plots, there was more variation between the groups than there was within the groups. So when you think of your F-test statistic, so the mean square group over mean square error. Okay, so basically we're looking for the variation between the groups over variation within the groups. Okay, what do your box plot be? Which one of these two numbers is going to be bigger? Okay, so did we have more variation between the groups or more variation within the groups? Okay, more variation between the groups. So I guess let's write this up. Between and within. Okay, so we have more variation between the groups and within the groups, which means that we're going to have kind of bigger numbers over smaller numbers. And when you have bigger numbers divided by smaller numbers, what kind of numbers are you going to get? Bigger numbers. Okay. So if the population means are different, we would expect big F values. So big values of our test statistic if the population means are equal. Okay, just because we'll have more variation between the groups than we have within the groups. Which means that if my population means are the same, what would you expect from your F statistic? You would expect small values. And how do we decide how big or small our F value is? Do you think? Okay. Just like with when we wanted to do our one sample z-test, and we want to see, well, how far is the sample mean? Is that really far away or not? We had it to scale. And we ended up going and finding the p-value. So just like that, now we'll find the p-value to decide if that F statistic is really big or not, significantly big. So let's go through the official stats for the ANOVA F test. So when to use it, if we want to compare several population means. And we have some assumptions. We're not really going to check the assumptions on these. Okay? I know I made you check assumptions on every test. But for this one, because it's difficult to show you everything you need for it, we'll just kind of go with the assumptions on it. Okay, but the assumptions are that your population variances are all approximately equal. Okay. Some rules of thumb say one shouldn't be more than double the other one. Some say one is not more than 5 times the other one. But your standard deviations or variances are all approximately equal. Okay, the populations are approximately normally distributed. Now, ANOVA is pretty generous with this, as long as it's just kind of mound-shaped and fairly symmetric. It's okay with it. And your samples are independent. Remember we said the null hypothesis is that all of your population means are equal, whereas the alternative, the opposite of all the means are equal, is that at least one of the population means is different. We have our test statistic, mean squared group with a mean square error, and 2 degrees of freedom. So we did talk about the F distribution once before in this class, if you remember, and the F distribution has 2 degrees of freedom, where K is the number of groups and is the total sample size. Okay. The p-value is the area under the F curve to the right of our test statistic. Why are we doing only the right tail? Okay. It's because of what we wrote down on the first page. If our population means are not equal, then we get bigger and bigger values of the test statistic. So the bigger and bigger F gets, the more and more likely it was when you had your unequal population means. And so that's why we only care about the right tail. So this one is always a right tail test, which is different from what we've done so far. And then as far as ANOVA, it would be really painful to try and calculate by hand. So we're going to use the computer for everything. This is a typical ANOVA table, so you'll have your groups, also called treatments, depending on which computer program you use, your error, sometimes called residuals, and then your total. It'll tell you degrees of freedom, sum of squares, lots of times they'll just switch those 2 columns. Okay. It'll tell you mean square, your F test statistic, and your p-value. And the last thing to look at is your coefficient of determination, which is R squared, and it's SSG, so sum squares group over sum squares total. And R squared tells us the percentage of variation that's explained by the differences between the groups. Okay? And the rest of the variation comes from the individual variation among the people within a group. So we'll use that in a problem and then it will make sense. So for example 1, we have a sample of 134 students was taken. They were broken into groups based on how many Facebook friends they have, and they were then given a social attractiveness score. Is there a difference in the population mean social attractiveness score based on how many Facebook friends a person has? So we want to conduct a hypothesis test and find and interpret our R-squared. So first of all, look at this output. So you have your groups. So your groups are 102 friends, 302 friends, etc. So we have 1, 2, 3, 4, 5 groups. And we wanted to know are the population means different between the groups, which is why we need to use ANOVA. We have our sample sizes and our sample means for each. Okay? So it looks like we range from 3.82 to 4.88. And our question is, okay, there's some differences in the sample means. Are those differences significant? Okay, did they happen just based on what sample we chose, or do we really have different population means to start with? Okay. What do you think, just looking at that thought spot? This is fairly close to me. If one of them was going to be different, which one might you think is different? Okay. Maybe the first one is a little bit lower than the rest, but I can't really tell visually, which is really why we need our numerical methods. So this is our ANOVA output from the computer. Notice, again, it will give us kind of that similar table where it tells us each group, the means, the sample sizes, and the standard deviations. The last row is the total, so if you throw everything into one data set, you have your total means, total sample sizes, and total standard deviations. And then the ANOVA table. So treatment is what we call the group. And error, you have sum of squares, degrees of freedom, mean square, your f-test statistic, and the p-value. So when we want to do our ANOVA test, because we're using computer output for it, we're going to skip quite a few of the steps, but we still need to know what is our significance level. Did they tell me significance level? Looking at a problem statement? Okay, I see some people shaking their heads. I don't remember, so we'll go with 0.05. We do need to know our null and alternative hypotheses. So the null hypothesis is that, and specifically all means are equal. Okay, and the alternative is that at least one is different. Do we know which one is different? Or how many are different? No, just that at least one is different. Now, aside from ANOVA, we're not going to check the assumptions, mostly because most of the problems in your book and things that are given, you're not actually given like all the histograms or normal quantile plots and things to actually check to see if it's normal, and it doesn't always do a good job of telling if you're independent. So as far as this, know that there are assumptions, but for all of your homework and everything when you're looking at the book, they don't always tell you whether or not they're met, so we'll just go with a kind of assumption that everything's met and we can do ANOVA. So next step is we usually skip we do our test statistic. Which is really easy for ANOVA because we just read it off the table and f equals 4.14. And not only that, but when I want to find my p-value, I just read it off the table and it's 0.0034. So, is that a big or a small p-value? A small p-value, smaller than our alpha. So we're going to reject the null hypothesis, which means what? Let's see. So 0.0034, that's our very strong level, so we found very strong evidence that, how do you want to phrase this? Put it in the context.
At least one mean is different from the others.
Okay, at least one mean is different from the others. Put it into even more context of this problem.
There's a difference in the mean social attractiveness score based on how many Facebook friends a person has. That's long.
It is long, which is why I was also talking about showing if I'm running it up here, but there is a difference in the mean social attractiveness score based on which group they're in. But really all we know is at least one group is different. We don't know which group is different, right? So we found very strong evidence that there is a difference in these group means, that at least one of the group means is different from the others. We also want to find R squared. So if you look back at the previous page, what was the formula for R squared? SSG over SST, right? So we just need to pull both of those values off our table. So SS group, sum squares group, would be our 19.89, and sum squares total would be 174.75. So about 0.114. So what R squared tells us is it tells us what percentage of the variation in the data is explained by which group you're in, and then the rest is just explained by variation within the groups. So we can say something like, so 11.4% of the variation in social attractiveness scores is explained by which group they're in. And the rest of the variation is explained, or the rest of the variation is explained or caused by just the individual variation that naturally occurs from person to person. So that was actually an incredibly low R-squared value. Okay. So even though we did have a small p-value and we did say that we're very sure statistically that there was a difference in the population means, now we can say, okay, well, so 11.4% of our total variation, okay, in our scores is explained by which group you're in. And the rest is just caused by the natural variation from person to person. So really, which group you're in isn't causing a ton of variation here. So even though we're sure groups have different population means, it's not making that big of a difference. Okay. So it's not a direct translation, but I kind of think of it as the difference between statistically significant and practically significant. It's kind of along those lines. So that's everything I'm going to ask you for ANOVA from start to finish. Any questions on it?
So this doesn't really tell us like causality between the two, right? Because we can, I mean, based on like their social attractiveness, they could have more or less Facebook friends. You know what I'm saying?
Okay. Well, this one is more of, so we could, if you have independent groups, you could try and show causality here, but because our groups are the number of friends, then we can say we could try and determine your social attractiveness score based on how many friends you have. Okay. However, the thing that tells you how good your predictions are going to be is your R-squared value. Okay? So we want R-squared values that are close to 1. If your R-squared values are close to 1, then that means you could get good predictions off of it, kind of. Because our R-squared value is so low, that means we're not going to get very good predictions because there's so much of the variation, about 89% of the variation is just caused by variation from person to person, not by which group you're in. So we could try and use the group. the number of friends who predict your social attractiveness score, but we're not going to do a very good job. It's kind of what the R-squared value tells us. Does that answer your question?
Yeah, so if it's high, then we can predict it a lot better.
Yes, you'll be able to predict it a lot better. Okay. We don't usually predict things off of ANOVA, but technically it is kind of that idea of you could try and predict your score based on the number of friends you have. So other questions on ANOVA? Anyone see one problem? I think it's not too bad. Hopefully you agree with me. Okay. So pairwise comparison. So all we are able to tell on the ANOVA is just whether or not all the population means were equal. But if they're not all equal, ANOVA doesn't tell us where the differences are. It doesn't tell us how many are different or which ones are different. If you want to know which ones are different, you have to go on and do what's called a post-hoc analysis because you're doing it after the fact. And you only do this post-hoc analysis if ANOVA tells you that there are differences. So you always do ANOVA first, and if there's differences, then you can go on and look at what we call pairwise comparisons. And there's a few different ways to do it. The most famous ones or common ones are the two-key multiple comparisons. And we're not really going to focus on this. It doesn't pop up really in homework very much or anything. But I did want to show you just what one might look like. So this is a megastat output. Okay. We're going to use alpha equals 0.5, and we're looking at this, and we just want to know, okay, well, which groups are significantly different from the other groups. So notice it does set it up so all the groups are down one side, all the groups are across the top. Okay. Why are the top squares empty, do you think? It would be redundant, right? You don't need to do 102, 902, and 902 and 102. Okay? So the top is empty because it would be redundant, and also you don't need to compare 102 and 102 because obviously they have the same population mean since it's the same set. So just looking at these numbers, what would be intuitively, which ones do you think have different population means? The ones with the small p-value. So which ones have small p-values less than 0.05? This one, this one, and that one. That's all of them, right? That have p-values less than 0.05. So we could do the mean for, let's say, 102 is not equal to the mean for 502. Statistically significantly not equal to them. Let's see, and the mean for 102 is significantly not equal to the mean for 302. And the mean for 302 is significantly not equal to the mean for 902. So those are the only three pairs that show up as being statistically not equal. I did include the little dot plot that automatically comes with ANOVA and megastat. And let's see, so if we look at 102, it was statistically significant from 302 and 502. Which makes sense because those are the two highest values. They would be the ones furthest away from 102, which is the lowest value as far as the sample means. And let's see, 302 is statistically significant from 902, 302 and 902. Well, that's a fairly big difference. I can see why that might have been the difference that was statistically significant. But basically, that's all that happens for your post-hoc comparison is you just tell ANOVA, okay, go ahead, run the post-hoc, and it'll give you a table like this, and you can just pick out which pairs are not equal to each other. So, not too bad. So, for example 3, the length of flowers in millimeters are compared for 3 species. Are their mean lengths the same? Conduct an appropriate hypothesis test and find and interpret R-squared. Okay, just looking at the box plots, what is your feeling on this? Probably definitely not the same. That's what I think. Let's go ahead and do all of our numerical results though. We'll start with an alpha. Let's use 0.05. we need our normal alternative hypotheses, and I know it gets tiring running the same thing each time, but let's see. So the null hypothesis would be that the mean population mean for Baha'i equals the population mean for red equals the population mean for yellow. And the alternative is that at least one population mean is different from the others. The next step is always going to find our test statistics. So what is my test statistic for this situation? Just look at the table and it is 259.12. That is a big test statistic. If I saw one that big, I probably wouldn't even need to look at the table to know that that's going to have a really small p-value. And in fact, our p-value is 1.92 times 10 to the negative 27. Okay, very, very small p-value. Okay, and so that's a small p-value. We will have to reject the null hypothesis. And so we have extremely strong evidence that what? I guess I should go back up and read the actual problem statement. The lengths of flowers in millimeters are compared for 3 species. Are their mean lengths the same? Conduct an appropriate hypothesis test. So extremely strong evidence that at least one of the population mean lengths is different from the others. Based on which species they were. And I guess I should write a little bit smaller. Now we need to find R squared, which is some squares group over some squares total. So 1,080, so some squares group over some squares total. Remember, treatment is the group. So we divide by 1,189.4381. So now our R squared is 91. So what does that mean? That means we can explain 91% of the total variation in lengths by which species they are. And the rest of the variation comes as just natural variation from flower to flower. Okay, so if I can explain 91% of the total variation in length by which species they are, that means that my predictions would be a lot better. So based on which species they are, I could tell you maybe what length they might have. Notice that there was a big difference between this r squared and the r squared in the last problem. And again, just another note, because we can't say it enough, ANOVA only tells us at least one of the population means is different. It doesn't tell us how many or which ones. If we want to know that, we have to do a post-hoc analysis. And your book goes into great detail on the post-hoc analysis if you want to know formulas and things like that. So for 4, I don't know, do you guys really need to do another one? I don't think so.
Should be different, put anything different.
No, because my p-value, I was wondering if I put one on with a big p-value, but this p-value is still small enough to reject, so we can say that at least one of the types of gasoline has a different population mean from the others. So it is pretty basic. So these notes came from my 2000 class, and I usually baby them a little bit more. Okay. So for this example, again, small or big p-value. Small p-value, which means that at least one of, we reject it, and at least one of these population means is different based on which type of recorder you have. Oh, I will do this one with you though. Okay, so let's practice pulling values from the table. Just use the display ANOVA table from above. Because it could come up in your homework or the test, I might ask you to tell me things like the group mean square. So if you want to know the group mean square, just come back up to ANOVA. So we're using this ANOVA panel. Okay, remember treatment is your group row. So group mean square is $250. Point what? Is it? 0.83. Okay, total sum of squares. To do total sum of squares, total sum of squares for S, that looks like 574.92. Total degrees of freedom? 11. Okay. Sum of squares for our error. 74.75. Mean square error. 8.306. Group sum of squares. 500 what? Error degrees of freedom. 9. F-test statistic. 30.11. P-value. 0.0001. Okay, so that's ANOVA. Pretty simple. Okay, Alex is pretty simple when explained this way.
So on the test, whenever you give us these tricks and stuff, do you want us to go step by step like you did in the first 2 examples, or can we just look at the p-value and say, yeah or nay?
I would probably, for this, if I wanted it, I'd say specifically, so I'd say, okay, tell me what your hypotheses are, step 1, step 2, tell me your statistic, 3, p-value, and conclusion is kind of what I might do. Or I might just say, jump straight to the conclusion, because for ANOVA there's really no work, it's just, can you tell me your conclusion? So I'll probably ask you hypotheses and conclusion.
Are we ever going to have to calculate those values on our own, or will we always have a table?
Not in my class, so I just think it's silly to try and calculate it by yourself. So you always have a table, which is why ANOVA was a pretty short lesson. So if we go to section 11.2, we're still going to deal with ANOVA, but we're going to add in just one more complexity factor. Okay. So we're going to do randomized block designs. So if you remember in chapter 9, we learned about independent samples versus paired samples. Okay. And why did we use paired samples? Let's say louder.
To compare 2 samples.
Okay, we use the paired samples to compare two samples, but what was the benefit of paired samples versus like independent samples? Eliminating bias, right? So instead of like taking 10 cars to garage 1 and 10 cars to garage 2, we took all of the cars to both garages. And so that way, you don't have to worry about the effect from like car to car or from person to person. So just like we did paired samples last time, it makes sense that for ANOVA, who have more than 2 samples, we might want to have something analogous to paired samples. And the way that we do that is with block designs. Okay, so let's say we're interested in the effect of a new drug on inducing a temporary reduction in a patient's heart rate. So we want to compare 3 levels of the drugs, low, medium, and high. So how could you control for the difference between patients? Okay.
Just match people based on similar characteristics or traits or something like that.
So
Hopefully one period of time is to people.
we can match people and give the similar people each dosage or each level. And we talked about doing that last time because we didn't want the drugs to interact. Now, the people that did this study is they said, well, because we're only looking at a temporary reduction, instead, it will be okay to give the same person each their levels. We'll just wait so long between each time to let the drugs out of their system. And also, because maybe the order that you're giving the effects in might matter too, they randomized the order that each person was given each dosage and waited long enough that they didn't get the carryover effect. So in this case, they're going to give each level of drug to each patient, but wait long enough that it's okay. And because they do that, then you don't have to worry about just the difference from patient to patient. So here are the results. So notice they had 3 drug levels and 3 patients. Okay. 8 patients. So for each drug level, they had the average reduction in their heart rate. So average for low people was 21, medium people 29, 32, etc. And then they each had information, also have information for each patient. So each patient has an average on all the levels, and you have your grand average. Okay, so your treatments are again kind of your groups or the treatment they actually give them. That's why it's called treatments, because it usually comes up in something like this, a medical case where you're treating them. Okay, so we have our 3 levels. So we are going to say K equals 3. And we call the 8 patients our blocks. Okay? So we have B equals 8 blocks. So we conducted it as usual, but we now have one extra thing to consider, the blocks. Okay, the null hypothesis is, our main null hypothesis is still going to be that the means for each treatment are equal, whereas the alternative would be that at least one treatment has a different mean. Now luckily, it doesn't get any harder to interpret our conclusion. Okay. Notice the table looks the same except for what happened. They added in an extra row for the person. So you still have your treatment, which is your dose level, and then you have your block, which is your person. Okay. But if I ask you what conclusion could you give for the main question of whether the 3 dosages have different effects? So if you're interested in whether or not the dosages have different effects, you just look at the p-value for the dosages. That's all you have to look at. That's 0.001, so is that a big or small p-value? Small, no matter which alpha we pick, that's a small p-value. We reject the null hypothesis, and we have evidence that the mean reduction is different for at least one of the dosage levels. Okay. So notice that question wasn't any harder to answer even though we threw in the extra complication of the blocks. Okay? So what they did is they basically, it's built in, so automatically controls for the difference from patient to patient, and you don't have to worry about that anymore, and you can just say, okay, we just have evidence that the mean reduction is different for at least one of our dosage levels. Okay, so as far as you interpreting it on the exam, it's not any harder than when we just did plain ANOVA. Okay. But, interestingly enough, so we can look at the difference in our levels, but we can also, because we did all this work, we can also look at the side question, what we didn't care about quite so much, but could be interesting to us still, is did the effects vary from patient to patient? So if you want to look and see if the effects vary from patient to patient, you go back up to the ANOVA table, but instead we're going to look at the block or person row. And it has a p-value of 0.009. And we reject the null hypothesis. But I'll say this, there were two different null hypotheses. There's a null hypothesis for the levels of the dosages, and there's a null hypothesis for the patient to patient. So because we reject the null hypothesis, then we can say that we do have evidence that the mean reduction is different for at least one patient. I can't tell you still how many of the patients are different or which patient is different, but we do know that the mean reduction is different for at least one patient. Now the reason this might be interesting to you as a scientist if you're doing this study is you look and you say, okay, so I looked at the first part, and that tells me that yes, my reduction level will depend on which level of dosage I give them. That's important to know. But you should also look at it and see, okay, it varies quite a bit too, just based on who the patient is. So that's something you can keep in mind, that it will have different effects on different patients. So any questions here? This next question that we're going to look at is actually very famous. I think I haven't researched this in depth, but from the different pieces of stories, I think that this is from R.A. Fisher, and I think that this is where the randomized block designs come from, and I think it's why we have the term blocks instead of like patient or something like that. So he said, we want to compare the average yield for 4 different types of wheat. Okay? But what might happen if I just put one type in Johnny's field, one type in Ben's field, and I put one type in each field? What could you see going wrong with this experiment?
You don't know what the soil is like.
I don't know what the soil is like.
If they water the way they should.
If they water it, maybe even as far as like what the sun is, there could be all these differences. And so he realized that I might think that the wheat type A wheat grows better, but it might just be because it was in this field that got more water. And so we realized that we're going to be introducing a lot of bias if we just put one type in each field. And so it makes a lot more sense if we put each type, or if we put all 4 types in each field. So what he proposed is that we partition each field into 4 plots and put each type in one of those 4 plots so that each field has all 4 types of wheat. Okay. So in this in this situation, how many treatments or groups do you have?
5.
Okay. So we have treatments and blocks. So treatments is kind of the thing that we'd be most interested in, comparing like what's the most effective, and then the blocks are like where we actually put stuff or who we actually tested on. So our blocks is the 5 fields, and our treatments, or like what we're really interested in, is the types of wheat. So we have 4 types of wheat. Now I've asked you here, what are your null and alternative hypotheses? Now technically you can have 2 different sets. You have the mean question of interest, and then you can also have your side question of interest. What would be the main set of hypotheses that you really want to test?
Types of
The types of wheat. So, the means are equal for the 4 types of wheat. And the alternative would be that they are not all means are equal. Or at least one is different from the others. Why is that my main question?
That's what we really want information about.
Because that's what we really want the information about. Okay. Because that was the whole reason we're doing a study, so that's why that's my main question. My side question could be, are the means equal for the 5 fields? And the alternative is that at least one mean is different. Okay, so we have 2 hypotheses, and luckily our tables just gives the p-value for each one separately. It's very easy to use. Okay. So what conclusion could you give for the main question of whether the wheat type has an effect on average yield? So we have our treatment, which is the wheat type. The p-value is 0.6766. So how do you feel about that p-value? You said it's big? And what do we do with big p-values? Reject. Now remember, we still always give our conclusion in terms of the alternative hypothesis. So what we're going to say here is that because we failed to reject it, we just didn't find enough evidence to conclude that not all the means are equal for the 4 wheat types. Not enough evidence to conclude that the mean yield the mean yield differs based on the wheat type. Okay, so really, we just didn't find any evidence that the mean yield differs. And in fact, that was a really big p-value. So I feel pretty safe saying that the wheat type's not making any difference here. Now, what conclusion could you give for the side question as to whether the average yield varies from field to field? So from field to field, that is our block, so it has the p-value of 0.0005, which is small, so we will reject its null hypothesis. So in fact, we have extremely strong evidence that the mean yield is different for at least one field. Isn't that interesting? So we have the wheat types didn't make a difference, but the field made a difference. Okay. Now again, we don't know how big of a difference necessarily, but we're very, very sure that there was a statistically significant difference. or at least one of those fields. So that is everything we're doing for ANOVA. Any questions on it? We're really just focusing on looking at the computer output and being able to interpret it.